Good afternoon, everyone. So we'll be starting our today's afternoon session. So we are very lucky and feel honored to have internationally renowned personality, the academician scientist with us, Professor Susmita Mitra from ISI Kolkata. Okay. Now I'll request Dr. Palas Gosal, Program Coordinator, to welcome ma'am with traditional way of Sikkimese by offering khada and memento. Thank you, ma'am. So I am honored and privileged to introduce ma'am with very few lines, because ma'am has a very dynamic role played in academics and research. So if I go through line by line, it will be take too much time. Okay, so I'll just quickly brief the highlights of the ma'am contributions and just a brief about the ma'am. So Susmita ma'am is a full professor at Machine Intelligence Unit, Indian Statistical Institute, Kolkata. From 1992 to 1994, she was in RWTH Germany as a DAT fellow. She was a visiting professor in the Computer Science Department of University of Alberta, Canada, Meiji University, Japan, and Aalborg University, Denmark. Dr. Mitra received the National Talent Search Scholarship in 1978 to 1983 from NCERT, India. The University Gold Medal in 1988. The IEEE TNN Outstanding Paper Award in 1994 for her pioneering work in neuro-fuzzy computing. The CIMPA INRA UNESCO Fellowship in 1996, and Fulbright Nehru Senior Research Fellow in 2018 to 2020. She was the INAE Chair Professor during 2018 to 2020. Dr. Mitra has been awarded the prestigious J.C. Bose National Fellowship 2021. Dr. Mitra ma'am has authored several books like Neuro-Fuzzy Pattern Recognition, Methods in Soft Computing, and Data Mining, Multimedia, Soft Computing and Bioinformatics, published by John Wiley, and Introduction to Machine Learning and Bioinformatics by Chapman CRC Press, with other edited books. Dr. Mitra has guest edited the special issue of several journals as an associate editor of IEEE ACM Transaction on Computational Biology and Bioinformatics, Information Sciences, Proceedings of INSEA, Computers in Biology and Medicine, IEEE Transaction on Fuzzy Systems, Neural Network, and is founding associate editor of Wiley Interdisciplinary Reviews, Data Mining and Knowledge Discovery. She has more than 150 research publications in referred international journals. Dr. Mitra is a fellow of IEEE, the World Academy of Science, TWAS, Indian National Science Academy, International Association for Pattern Recognition, Asia Pacific Artificial Intelligence Association, Fellow of Indian Academy of Science, Indian National Academy of Engineering, National Academy of Science of India. She serves as a member of Inter-Academy Panel of Women in STEM. She has visited more than 30 countries as a plenary invited speaker or an academic visitor. She served in the capacity of General Chair, Program Chair, Tutorial Chair, or many international conferences, was the Chair IEEE Kolkata section, and IEEE CIS Distinguished Lecturer. Her current research interests include data science, machine learning, soft computing, medical image processing, and bioinformatics. So this is just, I have given the highlighted point, okay, it has many more to say, but I'll just introduce with this brief. So thank you ma'am once again for coming here and giving your thought and insights to our participants. So please ma'am, welcome.
First of all, I thank you, sir, for those very kind words introducing me. I thank Dr. Prof for inviting me to this school. And a very good afternoon to all of you after your lunch. And I hope you don't fall asleep. Okay, so of course, maybe some part of it will be repetitive because you have already been introduced to basics of AI. But anyway, I'll try to give you what I thought I should tell. Okay, so introduction to AI. So what I will cover is learning, neural learning and deep learning. So AI obviously has many other aspects. Artificial intelligence today is the catchword. When we were students, we used to do the search algorithms, A star, and then those languages like Lisp and Prolog. But today, the scene has changed, and today you have more focus on these aspects. So let us focus on that. So learning is a very inherent part of every living being. We human beings also learn. So when a child is born, it learns to talk, it learns to walk, it learns to do everything, and it tries to perform by looking at the data around, that is its parents, the neighborhood, other people, tries to pronounce some word or tries to take the first step, then it falls down, the child. Every one of us have gone through that stage of childhood. So we take our first steps, we fall down, then again we try to correct what went wrong and try to modify and take the next step, and this is how we all learn to walk, we all learn to speak, and we listen to our parents, and then they correct us, and we minimize some error, which is the objective function, and that is how the world goes on. So in neural networks or in AI, we try to mimic this learning scheme of the living world. So that is learning. Learning has been going on in computer science or even in signal processing, in electrical engineering for long. You had the core topic of pattern recognition. There also you had learning. After that, as the amount of data started increasing in the internet, you had this terminology, the topic called data mining. There also you have learning. And today you have data science, you have AI, you have machine learning. So basically it is all old wine in new bottles, and the scheme, the presentation has changed. You have much more data obviously, and the environment is different. So what is learning? A teacher is involved, teaches the students, that is learning. Learning can be of two kinds. One is supervised learning, where there is a teacher who teaches. That is, you know what the correct output should be, and you try to predict something, and based on the error from what the correct output should be and what your output or the machine's output has been, that error is minimized such that the system tries to perform better. So supervised learning can be of two kinds, basically classification and prediction. So what is prediction? Prediction is regression rather. In mathematics you have regression. Y is a function of x. So these x's are the input variables and y is a function you are trying to predict. There also you have an error which you try to minimize. And you know what the y should be, and you try to minimize that error between the predicted y and the actual y. And that is minimized so that the parameters get changed and the learning occurs properly. In classification, on the other hand, y is a class level, whether it belongs to this class or that class. So these are categoric class levels, while in prediction it is a numeric value. So based on a training set, so in supervised learning you have a training set, and based on the training set the model learns, and after that, given an unknown set of data, it tries to see how it can perform on this new data. Some applications typical applications include in bank, whether credit can be given, loan can be given, medical diagnosis, treatment, how effective is a drug for a treatment. These are some practical applications of classification and prediction. Unsupervised learning, where you don't have any output information about the classes. There is no teacher involved. The system has to learn. So there is no supervision, there is no training data and testing data, but here the class levels are unknown, and given a set of measurements or observations, the aim is to establish the existence of homogeneous groups, which are also known as clusters. So how do you evaluate the classification methods? Based on their predictive accuracy, how good they are at predicting the accuracy for the unknown test set. Speed and reliability. Today, with the huge volumes of data available on the internet, scalability and speed are very important, because if you want to predict something, if you take 1 year to predict the output, that is of no value, absolutely. So given the large data, you should have the computing power, and your algorithm should be efficient enough so that it doesn't consume too much space and time, and it should give you output in real time. And some of the existing traditional algorithms may need to be modified for the large data of today. So in pattern recognition also we have classification and clustering, but today when you use that with the large data and the multimodal data, multimodal means numeric, linguistic, image, sound, audio, video, everything together. So it's very complicated. So it should be able to provide you output in real time. Then robustness. So some inputs are missing or there is noise, it should be able to predict. Scalability. How efficient it is in handling the disk resident databases, picking them up and working on that, and again sending the output back to the database. Interpretability, because the human end user is at the is the one who is using it. So the human end user doesn't understand ones and zeros, which the computer understands. So it should be understandable to the human end user, and that's what is called interpretability. So some insight should be, understanding and insight should be provided by the model. And how good are the rules? Suppose you extract some rules from the model. So if it is some kind of a rule like if so and so, and so and so, and so and so, and n types of such ands, then we lose track of what is happening. Human brain is limited, and the human end user is at the end of it. So the human user must be able to understand. So the rules that are generated should be compact. Now suppose there are two classes like this, which are well separated, and you can draw one line to separate the two classes. So this is a classification problem. So suppose there were input values, input features M, which were height, weight, complexion, diet, and so on, some others. And here you see, by just using height and weight, we are able to distinguish between the two classes. So we don't need any further complications. So this is the simple classifier design for this. So this is called a linearly separable problem. You can draw one line to separate between the two classes. So in such cases, you should not go for deep learning. Today the catchword is deep learning. So, but then when such a very simple model works, people should not go for deep learning, because it's just useless and waste of time and resources, and it does not give any meaningful result. But people today try to use deep learning thinking that their proposal will get through, but that is absolutely stupidity. Now the decision boundary between the classes, that is the D that we had, one line, it need not be a straight line, it can be of different kinds. You see, you can have a curved structure, convex, or you could have the piecewise convex, then you could have concentric boundaries, you could have overlapping boundaries, and so on. So you need different classifiers designed to handle this kind of situations. So classification, the goal is to predict the class given some inputs xi. Regression, you need to predict y equal to function of x. So classification methods are different kinds. You can have the nearest neighbor classifier, decision tree classifier, probabilistic or generative models like the Bayesian classifier of statistics, or you can have neural networks. This is the nearest neighbor classifier. Suppose you have two sets of points, the brown points and the blue points, and this white point is the unknown point. You want to give it a class based on these two classes. Now, the nearest neighbor classifier tries to compute the distance of this unknown point from all the other samples there. And if you call it one neighbor, then it will compute the shortest path, the nearest sample, and assign it to that class. If you have k nearest neighbors, where k is typically an odd number. Why odd number? Because then you can have a voting, otherwise there can be a tie. So if there is a tie, you have no solution. So if k is odd, so the majority classes which are near to it, it will be classified to that. For example, here we find that there are 7 brown points and 2 blue points to this unknown point. So obviously it is classified to the brown class. So that is what is the k nearest neighbor. Here it is 8, this is 4, 7. So you are computing from 8 neighbors. Typically you should compute from odd numbers, because here if there were 4 and 4 from both classes, you would have a tie and no solution. This is a decision tree. A tree structure is constructed. You see, given a table, of course this is a play problem, because it's a very simple problem, very simple table, but in real life, in database, it's not so simple. You can have n number of columns, n1 number of columns and n2 number of rows, which are very high, and it's not visualizable by the human being. So then you need this kind of decision tree, gives a very meaningful understanding. For example, here what they are trying to do is, based on the salary and the education level of a applicant, the bank is trying to decide whether to give a credit or a loan or not. So from this decision tree that has been constructed from this table, relational data, it is obvious that it is something like, if the salary is less than 20,000, then you come down to the next level, then you test the education level. If it is a graduate, then you accept the loan application. If it is not a graduate, then reject the loan application. And if the salary is greater than 20,000, then automatically you are accepting the loan application. This is based on the data, just a rule. So the rule is more understandable. And the logic is that if the salary is very low and the education level is very low, then it's very likely that the candidate won't be able to repay the loan. It's something like that. So the inference is that when you have a decision tree like this, then it's very meaningful to the human end user to understand what is going on. But if you have just had the table, it would not be so clear to you what is the rule behind it. Then this is a neural network. Neural networks, this is a basic neuron with some inputs, with some weights, and it tries to compute an output function. And typically these neurons are combined together to get a neural network. So set of nodes are connected by directed weighted edges. Neural networks are useful for learning complex data like handwriting, speech and image recognition. So in linear regression, you construct a straight line, the decision boundary. In a classification tree or the decision tree, you construct those horizontal and vertical boundaries. and in neural networks you have the non-linear boundaries. It's more powerful. Now there are two problems associated with this, underfitting and overfitting in learning. Underfitting means you do not have sufficient data to train. So the model gives improper performance. It doesn't learn anything. So suppose you have just two samples and you wanted to predict something else. It may not perform properly. And that is true for humans also. What humans cannot do, machines cannot do either. Because if you are shown a sample of a chair, suppose a child is shown a sample of a chair and never shown a table and given a table to identify, how can the child learn to identify that it is a table? So that is the problem of underfitting. Overfitting is when you train too much. So you may recall in mathematics you learn about least square fitting. So it's something like that. If you have too much training, you're just learning the pattern by heart, like dictionary learning. You're not learning what is actually happening. So that is called overfitting. And when overfitting happens is this kind of behavior can be observed. So as I said, in classification you have a training set and a testing set. So on the training set, as you train the red line, the error is gradually decreasing over the epochs or the number of nodes as you are increasing. And over the test set, that is the dotted curve, at one point of time the error starts to increase. So one should stop the training at this point of time, that is the vertical line. Beyond this there is overfitting and the learning is not proper. So that was about supervised learning. Unsupervised learning, you are given three groups, let's say, not three groups, some samples. Obviously this is very simple problem. We can easily see and understand that there are three groups. So what you need to do is minimize the intra-cluster distance, or within cluster the distance between the points should be as small as possible. And between two clusters, the distance between the points should be as large as possible. So they should be as separated from each other as possible. So that is called inter-cluster distances are maximized. So distance maximized means similarity minimized. Distance minimized means similarity maximized. Now let us say in a family you have got four members, typical family, father, mother, son and daughter. Now you can have two kinds of clusters here. Based on the age, then the father and mother belong to the same cluster, son and daughter belong to the same cluster. It can be based on the gender, then the mother and daughter belong to one cluster and the father and son depend to the other cluster, belong to the other cluster. So that means each clustering has some objective. Based on that objective, the clustering output can be different. A good clustering method will produce high quality clusters with high intra-class similarity or within cluster similarity and low inter-class similarity or between cluster similarity. The quality of a clustering result depends on both the similarity measure used by the method and its implementation. So what is the similarity method? The distance measure which is used. It's the inverse of the distance actually. So the distance can be Euclidean distance, Minkowski distance, or Cartesian, or the that what is it called, the chessboard distance. There are many other distances. The quality of a clustering method is also measured by its ability to discover some or all of the hidden patterns. Now, this is a remote sensing application. So, suppose they take the picture by a satellite. So, this is a picture of the Hooghly River, neighborhood of Kolkata. So, spot is a satellite image of Calcutta in the near infrared band. Of course, towards the end, I have some other pictures I will show you. And so, this is the river, and you have the Khiripur dockyard and the Garden Reach Lake, Howrah Bridge, Hooghly River. That is the Ganga river, the race course. So you see in the race course there is more greenery, so there is a different kind of reflectance on the near infrared band. Similarly, the cemented region, the water bodies, they have different reflecting capabilities. So there is a different impact coming up to the satellite sensor input. So based on that, you can get this kind of a map. Now the notion of a cluster can be ambiguous. So suppose you look at the first image, how many clusters? You can say there are 6 clusters, you can say there are 2 clusters, you can say there are 4 clusters. So how many clusters? That is also a complicated problem. That is also a problem by itself. So how many clusters there are? That depends on what you want, what the end user wants. Then even when the number of clusters are known, even then there can be problem. So K-means is a very well-known clustering algorithm, very simple and very popular clustering algorithm. Suppose you have the original points. As a human being, you would think that the green would be one cluster, red would be one cluster, blue would be one cluster. But the clustering algorithm starts with a seed point. You have given, let's say, k equal to 3 or 3 clusters. Then it will start with 3 seed points and then it will try to build the clusters. And based on which seed point it starts with, it can end up in optimal clustering or suboptimal clustering. So the left side is the optimal clustering. You see it has more or less come up with the correct kind of patterns. Whereas in the right hand side it's suboptimal clustering. So it has split the bigger group into 2 and the 2 smaller groups it has put into the same cluster. So then this is also a major problem even if you know the number of clusters. So I'm just trying to give you a brief overview of what is clustering, what is classification, what are some of the problems associated with it. And classification clustering concepts come from pattern recognition, which today we take into artificial intelligence, deep learning and so on. So that was about the basic learning, basic pattern recognition. Then we go to neural learning. Neural learning started in the 1960s. Before that there was pattern recognition, the learning. So learning is a very old concept. Neural learning. So it is analogous to the biological nervous system. It came from there, the artificial neural network. So in the biological nervous system, you have the cell body, you have the dendrites, there is the axon, there is a message, some neurotransmitter passes. Of course, I am not an expert on the biology, but this is what, as much as I understand. So these chemical flows, and depending on how much of the chemicals comes from the other inputs also, so this other neuron at the end, it fires. And when it fires, it also sends some output. This is how the some kind of activity occurs in the brain, the signals pass. So keeping that in mind, the computer scientists tried to design the artificial neural network to emulate the biological nervous system. So the impulse is triggered by the cell, it travels along the axon, releases the chemical transmitter, raising or lowering the electric potential. If it is greater than a threshold, it causes a pulse. Neural network, analogous to it, is not programmed, it learns by examples, it's non-parametric. It is found to be more efficient than powerful digital computers or number crunchers in cognitive tasks. What is a cognitive task? So cognitive task is something which involves understanding, like which human beings can do much better than the supercomputers. An example, suppose you meet your friend with whom you studied in school. After 25 years or 30 years, you will still be able to recognize your friend based on some features. Although the features may have changed drastically, maybe the hairline has gone receded, the friend has become fat or thin, or the structure has changed, but still we are able to recognize. But if you were to feed a computer, a supercomputer, with a 17-year-old person and a 57-year-old person, it won't be able to match. But you as a human being will be able to understand. So that is what is called cognitive understanding. And in this kind of things, human beings are more powerful. So the ANN or the artificial neural network researchers thought that this must be related to how the biological nervous system works, and that's why the artificial neural networks were designed. So neural networks, unlike the conventional computers, are not programmed, they learn by examples, they are non-parametric. They are more powerful, efficient than digital computers. Now, the normal conventional computer is straight line, so it's not linearly solvable. So, Minsky and Papert showed that perceptrons don't work when it's linearly not separable. So then research in neural networks reduced until in 1980s when neural networks or connectionist networks were revived through the work of Rumelhart, Hinton and Williams, and this Hinton this time got the Nobel Prize, as you will know, in physics. So that was the first work of Hinton. But he was of course also associated with others, but only he was given the Nobel Prize. Then around that time, Fukushima in Japan was experimenting with the neocognitron model. And if you care to look up neocognitron in the internet, you will find that the structure is very similar to the convolutional neural network. So this Fukushima was beyond his times. In 1980s you did not have GPUs, you did not have so much computing power. So his models could not be implemented. So that concept died out gradually. But actually I would say neocognitron was the forefather or the initial ancestor of today's convolutional neural network. He designed it based on the mammalian vision system, and he was followed by the multilayer perceptron and backpropagation of errors by Rumelhart, Hinton and Williams, as I said. So this multilayer perceptron could solve the linearly non-separable problems also, and that was the multilayer perceptron which again opened up the domain of neural learning. This is the neocognitron picture of those days, 1980s. So you can see there is a very big similarity with the convolutional neural network architecture, but it was so complicated nobody could implement it. But today everybody can. But it died a natural death. Rise and fall of neural network research. So Rumelhart, they started in 1986. Again with the advent of kernel machines, the interest in neural network went down a little bit. But Jan LeCun, who had from 1988 gone on deploying neural networks for various tasks like handwritten text recognition, he was going on working on this. And then as he was working, he didn't have that much resources, but still he continued working, and today he is also famous. So the general framework of neural networks, you have processing units, you receive input from connected neurons, compute an output value and send it to other connected neurons. You can have input node, output node and hidden node. So the output is a function of the input, and there is a threshold or a squashing function, and the connection weights between the pair of neurons. If it is negative, that means the one neuron is inhibiting the other. If it is positive, then it is exciting the other. If it is zero, it has no impact. So they learn from examples, generalize from previous examples to newer unseen ones, and they abstract essential characteristics from the input, and they can be feed forward or feedback. Feedback is recurrent. There are different learning paradigms in neural networks. Again, those same paradigms, supervised, unsupervised, and then you have another which is reinforcement. Reinforcement is between supervised and unsupervised. So there is some kind of a reward if there is a correct output, but the output is not shown, just a reward is given. So it's some intermediate between supervised and unsupervised. There are various learning rules, the error correction, which was used in the backpropagation learning. Then you have Boltzmann learning, where the temperature concept comes in, Hebbian learning, competitive learning. Competitive learning is used in clustering mainly. Some of the popularly used neural network models, Hopfield's model of associative memory, that was one of the earliest models. Today you don't hear of that, but Hopfield and Hinton were jointly given the Nobel Prize in Physics this year because Hopfield was a pioneer. Then multilayer perceptron, Cohen's model of self-organizing neural network. Battery is running low, somebody has to connect it to the power. Somebody has to connect it with power. Are there nobody there? No. So then you have battery is running. Popularly used neural network models, yeah, then adaptive resonance theory, radial basis function network, neocognitive. So this is a perceptron block, basic block. So you have the inputs x1 to xn, the connection weights w1 to wn. You have a summation inside, there is a threshold, and based on its output, whether it is on the positive side or on the negative side of the line. So if summation wi xi is greater than theta, output is 1, theta is the threshold. If it is on the line, then it is that is the line of the decision boundary, and summation wi xi equal to theta, that is the separating line. So if it's less than 0, it's on the other side, and greater than 0, it's on the opposite side. Now when you combine a set of such perceptrons together, you get multiple decision lines. You can get a convex boundary, convex region, that is a class. Learning rule of a perceptron, the simplest possible rule. So the connection weight at t plus 1 is the connection weight at t plus the error. The error is given by a learning rate and the actual error and the input. So what is this error? It is the target minus the actual. So what it should have got and what it actually is, that is the delta. So if the sets of patterns are linearly separable, the single layer perceptron algorithm is guaranteed to find a separating hyperplane in a finite number of steps. And the rule is reward and punishment. So if it is correct, you are rewarding by not changing the weights, and if it is incorrect, you are punishing by updating the weights. Because this delta, the I, which if it is some value, positive or negative, that means it's getting a punishment, the connection weight is changed. And if it is doing correct classification, then that is given a 0 value, because the target minus actual will be 0. So you are not going to change the weight at the next iteration. So reward if correct by not changing the weight, and punish if incorrect by updating the weight. Now when you add multiple perceptrons in this manner, you are moving towards the multi-layer perceptron, and that is what is happening is you overcome the constraint of linear separability. Because when you have more layers, you are combining these convex regions, and when a combination of these convex regions is taken, you are getting a non-convex region. So the union of these two triangles would be a non-convex region. Multi-layer perceptron is after that, which is very popular, which was very popular until a few years ago. So you had the input layer, hidden layer, and the output layer. So up to that was machine learning, which is shallow learning. Shallow learning means the layers are not very deep. And once these layers in the multi-layer perceptron become deep, you have multiple layers, it becomes deep learning. And then you need even more data, even large volumes of data, and you need high performance computing, otherwise you cannot work. So AI is a program that can sense, reason, act and adapt. Machine learning is a subset of AI, algorithms whose performance improves as they are exposed to more and more data over time. Subset of that is deep learning, in which multi-layered neural networks learn from vast amounts of data. Machine learning, father is Tom Mitchell. A computer program is said to learn from experience E with respect to some class of tasks T, and performance measure P if its performance at tasks in T that is classification or prediction, as measured by P, which is the difference between the predictions and the actuals, improves with experience, E, which is the training data and variables. So machine learning is a kind of AI that provides computers with the ability to learn without being explicitly programmed, and it focuses on the development of computer programs that can change when exposed to new data. So you basically, in training, you have some labeled data which is fed to the machine learning algorithm. It generates the learned model, then some unknown data is fed to the model and it has to predict. Machine learning approaches, as we said earlier, it can be supervised, unsupervised and reinforcement learning. So deep learning is a branch of machine learning based on a set of algorithms that attempt to model high-level abstractions in data by using multiple processing layers with complex structures or otherwise composed of multiple nonlinear transformations. It achieves great power and flexibility by learning to represent the world as a nested hierarchy of concepts, with each concept defined in relation to similar concepts, and more abstract representations computed in terms of less abstract ones. So there, as you go higher and higher the model from the input to the output, the abstraction level increases and you are extracting more abstract features or the entire objects. At the lowest level you have the edges, let's say, and gradually higher and higher abstraction level occurs. So the traditional model of pattern recognition or machine learning, you had to extract some features. You had a handcrafted feature extractor. Suppose you have an image of a car and then there is a handcrafted feature extraction extracting the features, let's say the wheels and the door and the window and the engine and the so on. And then you feed it to a classifier. That is traditional pattern recognition, traditional machine learning or shallow learning. Whereas in deep learning, it's end-to-end learning. There is no expert involved, no feature extraction involved. The machine is doing it on its own. So the image is fed at the input and there is a trainable feature extractor and then there is a trainable classifier. So at the low level features could be some kind like this, the horizontal edge, the oblique edge, vertical edge and so on. The mid-level features could be the wheel, the structure of the wheel is gradually forming and so on. At the higher level, you can have even more complicated structures taking a shape. And finally, you have the trainable classifier. So higher layers of representation amplify aspects of the input that are important for discrimination and suppress the irrelevant variations. So suppose image is an array of pixel values. So the learned features in the first layer of representation could be the presence or absence of edges at particular orientation and locations in the image. The second layer could be detecting the motifs by spotting particular arrangements of edges regardless of small variations in edge positions. Third layer could be assembling the motifs into larger combinations that correspond to parts of familiar objects, and the subsequent layers could be detecting bigger objects as combinations of these smaller objects. Now the important difference is that these features are not handcrafted but automatically learned from the data. So deep learning has several opportunities. Obviously you can have different applications from photos, maps, voice search, ad targeting, self-driving car, machine translation, investment portfolio management, image recognition for healthcare diagnostics, image recognition for visuality impaired, speech recognition, industrial maintenance, sports performance and so on. Now all these algorithms, machine learning, deep learning, they use the typical gradient descent which we all studied. So gradient descent helps minimize an objective function parameterized by a model's parameters by updating the parameters in the opposite direction of the gradient of the objective function with respect to the parameters. The learning rate determines the size of the steps we take to reach a local minimum. There are three variants of gradient descent typically, which differ in how much data we use to compute the gradient of the objective function. So depending on the amount of data, we make a trade-off between the accuracy of the parameter update and the time it takes to perform an update. So it could be batch gradient descent or vanilla gradient descent, stochastic gradient descent and mini batch gradient descent, which is an intermediate of these two. Some of the challenges to gradient descent, as we all know, it's not a smooth surface like this with a global minimum. You have local minima and it could be stuck in local minima. Then you have to, the challenge is to minimize highly non-convex error functions, which is very common. Avoid getting trapped in the numerous suboptimal local minima. You have to perturb and get out of it to go to the global minimum. Okay, then what are CNNs? CNNs are a kind of deep networks. So let us take a step back to understand how traditional methods work. So this is what does a computer see? We see a bus. A computer sees an array of zeros and ones. So a digital image is a collection of pixels. Each pixel is a number representing its intensity. In color images, each pixel is represented by three numbers for the intensity of the colors red, green and blue. Traditional approach, shallow learning, typical pattern recognition, machine learning. You describe the object as a collection of shapes or characteristics. You train the systems to recognize those characteristics, find those in an unknown image, and then you have found that object. So you have to recognize that that shape of the car and the wheels and the windows and the doors and so on, and you fit it to the unknown data. But what about these vans? They have different orientation. Sometimes this kind of strategy fails also. Or these humans and the dog. If you have learned on the humans, the features, you may misfit on the other characteristics in that image. So Fei Fei Li, the director of Stanford's AI Lab and Vision Lab, she thought, how do children learn object names? Parents do not teach this by showing characteristics, but rather by naming the object or animal every time their child sees one. Maybe we need to do the same for computers. So Li and her team launched the ImageNet project in 2007. Collaborating with more than 50,000 people in 180 countries, they created the biggest image database in the world in 2009, which had 15 million named and classified images covering 22,000 categories in 2009. Now it has grown. So at that time, ImageNet has all these kinds of categories and all these subcategories of all these kinds of images, all possible kinds of images that she could collect by collaborating with people from around the world. Then there was the ImageNet challenge in 2017. They were provided, challenge means, you know, the challenge organizers give a training set. The participants are supposed to build a model on that, and then the models have to be frozen and submitted to the organizers. Then the organizers release a validation set, and how good your trained model performs on this validation set, that's how the winner is decided. So this 2017 ImageNet challenge had 1.2 million images from 1,000 categories along with ground truth. That was the training data. And the testing and the validation was on 1,50,000 images. In between, in convolution neural networks, as we mentioned earlier, Jan LeCun, who was going on working in the background with his MLP and his extensions. So ImageNet was just right for training a convolutional neural network. So as I said, these deep models need lots of data, otherwise it's meaningless. So this was the right opportunity with the ImageNet database to the ImageNet challenge to evaluate his convolutional neural network. This CNN, he was working on handwritten digit recognition. So his CNN had 24 million nodes, 140 million parameters and 15 billion connections. So as you understand, CNN with so much parameters, so these are all the variables that need to be learned. So if you give just 10 samples of data, obviously the system will not learn. So suppose you have a simultaneous equation, two sets of equations, two equations form a simultaneous equation. You have two variables which you need to find out. So if you have only one sample, can you ever solve that? So it's similar. So here you have so many equations. So all these nodes, they correspond to equations in unknowns, and you have to solve them. So unless you have millions and millions of data, it's whatever solution you find out is useless. It's just garbage. So people try to run deep learning with 100 samples. It's just toilet paper, nothing more. So this is the architecture, basic block diagram of convolutional neural network. So it's so complicated compared to the multi-layer perceptron. Convolutional neural networks have so many layers, and as you see, in different layers it becomes more and more complicated. So in 2006, the new algorithm, a fast learning algorithm for deep belief nets, was introduced by Hinton and his students. And the current boom in deep neural network research was fanned by this particular paper. This was a new algorithm. It proposed a method to build a large network of many layers, train each layer individually instead of all at once. Backpropagation of errors in a large network was made unnecessary. So they showed how to quickly and efficiently train a large deep neural network. Then came this GPUs. GPUs came with this paper by Rayana, large-scale deep unsupervised learning using graphics processors, and this changed the entire scenario. Powered by GPUs, you given the huge number of weights that need to be trained, huge number of samples are required for training. So this paper proved that graphics processors can be used to speed up learning process by at least 70%. Used NVIDIA CUDA GPU library to implement a highly efficient deep belief network. Compute unified device characteristics. Okay, so the parallel computing platform CUDA. This opened doors for training large DNNs that were previously impossible to train on CPUs. Then this challenge ILSVRC 2012, ImageNet competition, which is a large-scale visual recognition challenge where teams need to compete to correctly classify over 1 million images into one of 1,000 classes. So Krzyzewski, the student of Hinton, he won the 2012 challenge using a deep convolutional network. This was the paper. Winning the 2012 challenge, he absolutely thrashed the previous best error rate of 26% by achieving 15% error rate on this validation and test set. This sparked the interest of researcher communities to take up deep learning seriously, especially deep convolutional networks. So what constitutes deep learning? Deep learning consists of many ideas like deep CNNs, deep belief networks, deep Boltzmann machines, long short-term memory networks, recurrent neural networks and so on. But let us focus on deep CNNs only. So convolutional network is some kind of like this. You have the input and you have the feature maps in different layers, levels and the output. So shallow classifiers require a good feature extractor. It produces representations that are selective to aspects of the images that are important for discrimination. It is invariant to irrelevant aspects such as the pose of an animal, let's say. It needs handcrafted features. It requires considerable engineering skill and domain expertise. Key advantage of deep learning lies in automatically learning the good features. So the building blocks of convolutional network, you have the convolutional layers, which is the feature extractor, low to high level with larger depth and levels of abstraction change. Pooling layers, which are the downsampling. Then the fully connected layers which correlate the high level features with the classes. And there are other layers like the batch normalization layer as in AlexNet, dropout layer for regularization or generalization, and the max out layer. Evolution of CNNs. So this is the recent success of deep learning in the ImageNet challenge. Top 5 error on ImageNet classification challenge. So it is seen that as deeper networks were designed from the traditional SIFT to AlexNet, Overfit, ZillerNet, Oxford VGG was designed in Oxford, GoogleNet from CVPR. Today in computer science you need to publish more on the A-star conferences like CVPR, and then the ResNet. So human performance on the ImageNet was 3 to 5% and ResNet achieved 3.5%. So it was seen that the deep network was picking up, becoming as powerful as the human performance. So that is deep learning, deeper the better. As you are going deeper and deeper, you see AlexNet had 8 layers, then VGG 19 layers, GoogleNet 22 layers, and ResNet 152 layers. Here AlexNet 8 layers, VGG 19 layers, which came up in the 2014 challenge, AlexNet in the 2012 challenge. GoogleNet had 22 layers, and you see it was not just plain simple one straight line. It had other inbuilt configurations. So it's just going deeper and deeper is not that important. You need specific architectures also, architectural modifications. And then ResNet in 2015 challenge had 152 layers. It's no longer possible to fit it in this slide. Now, is learning better networks as simple as stacking more layers? So just stacking more layers doesn't give you better performance. So a 20 layer is that, so this is the training error. So with 56 layers the training error is found to be more on the CIFAR-10 database. And here the testing error also was higher for the 56 layer as compared to the 20 layer. So the 56 layer net has higher training error and test error than the 20 layer net. So just increasing the number of layers always does not help. Simply stacking layers, overly deep plane nets have higher training error, a general phenomenon observed in here in ImageNet 1000 and CIFAR-10 also. So up to that was, let us summarize, we started from learning to neural learning to deep learning, and now let's go to some applications of remote sensing. So hyperspectral remote sensing uses sensors to capture light across a wide range of wavelengths to create images. So image classification. So there are wavelengths, different wavelengths and different reflectance. So you see this is the land cover in a place in Japan, Minamimaki. So you see so this is the vegetation field, the Japanese cabbage, brown, Chinese cabbage, and these different vegetations are giving up different kinds of wavelengths, different kinds of reflectance values which are collected by the sensors, and thereby you are able to classify the different areas. So this is a vegetation field, and the different vegetations can be classified based on this remote sensing, hyperspectral imaging. Precise agriculture is an useful application, smart agriculture. So where and what kind of agricultural product will be produced? So which region will produce a better kind of a crop identification by taking these images. What quality of agricultural products will be provided for the market? What quality of agricultural products? Because the quality of the agricultural product can also be found out based on which minerals are coming up in that soil more, so which will make the crops better or of poorer value. All that can be analyzed in the spectral analysis model for the extraction of crop biochemical parameters. So precision agriculture is to do the right thing at the right place and at the right time. So it can provide relevant and reliable agronomic indexes to farmers. Precise agriculture, you see the amount of chlorophyll is measured here. Which area has what amount of chlorophyll based on the reflectance in the hyperspectral imaging. Then amount of nitrogen in the crop, in the field, based on how much there is in the soil and how much has been absorbed by the plant. Then dissolved sugar, leaf water content. So these are different biochemical parameter mapping. Color composed analysis, low protein content are these areas which are bad, which are the bad growing area, high sugar value, low TN, low chlorophyll. And high protein content means better growing area, low sugar, high TN, high chlorophyll. So thereby you can categorize a better area, and if it's a bad area, how you can improve the field just by looking at the image from the remote sensing, satellite image, hyperspectral images. So that is the application. Mineral exploration, spectroscopy, study of the interaction between matter and radiated energy, specifically looking at what wavelengths of light are emitted or absorbed by an object in order to characterize the materials. Mineral exploration, spectral histogram of the stratum. Then you are mapping that to get what kind of minerals are located in the soil. You can analyze. Urban and artificial objects detection. This is the hyperspectral remote sensing data in the northern part of Beijing city. So the urban and artificial objects, different characteristics, different colors are provided, and the satellite image can be analyzed by the scientists to come up with some decision or solution. Urban and artificial object detection. So classification, you can detect vegetation, water, cinder, asphalt highway, earth road, red tile roof, cement road or square, white tile roof, grey asbestos roof, and so on. Now, so much about deep learning, but there is a caveat of deep learning because deep learning has a terrible carbon footprint. Today, you know, we all want green technology, we want to reduce the carbon footprint. So deep learning is very much compute intensive, and running a GPU emits a lot of carbon. So the objective should be to design more efficient hardware which is lightweight, that means it can be computed fast, not going on for years and years. Develop more efficient algorithms. You know, if the algorithm is efficient, it will compute less power, it will consume less power. And the example of, the ideal example for this is the human brain, which can do amazing things with very little power consumption. So the objective of deep learning today should be to have efficient or lightweight models, not very huge GPUs, just. But of course, the performance goes down as you reduce the power. So that is the caveat, that's the offset you have to come up with. So with that, I end the talk today. Thank you, and I'll be happy to answer your questions. Yes.
A very interesting lecture.
Thank you.
From the basics. Ma'am, towards the end you were showing some imagery where you calculated nitrogen and other chemicals. So that was done in 2001. What kind of tools were available that time, or was it just purely?
I don't have any expertise in remote sensing, but because this is an application to remote sensing, this is related to remote sensing, I just got some slides,
Okay.
So I don't know about the technology.
Okay, no problem.
I work in medical imaging applications, so there also you see you have these images to predict, let's say, cancer and so on.
Yes. So ma'am, in medical imagery, in medical only RGB images are used or more bands?
No. There are other models also. There are other models also,
Okay.
and not only RGB. Color, that is color.
That is
And medical imaging, it's not always the visual thing, you know. You have these CT scans, MRI, PET. These are the multimodal aspects there.
yes.
Madam, in case of lung cancer, in earlier stages there was no symptoms found. So when the symptoms started to found, at that time lung cancer already in the fourth stage or final stage. Now, how is it possible for us to detect in the primary level of lung cancer through deep learning?
Here, in our country, with the large population and the burden on the hospitals, obviously we don't go for yearly health checkup, do we? We will never go because we don't want to stand in the queue and get the appointment, and when you are sick, only then we go. But in the Western countries, they have regular health checkup because their population is lower, their number of doctors dedicated to that, they have more time, so they can do that. We cannot afford that luxury unless you are able to go for a regular health checkup. So we will never find out unless there is a symptom, luckily. So if you find a symptom, that's lucky.
Yeah.
And mostly the village people, they try to neglect also. Poor people, they think that if I go to the doctor, I will spend so much money, but they don't understand that as it becomes more complicated, you'll spend even more money. So suppose there is the doctors say that when there is a persistent cough, you should go to the doctor. Do we go? We just try to take our own medicines. That's our fault.
Yes, ma'am.
So how can the system detect if you don't go for a picture? And if you go to a hospital and you say, let's take a picture, even the doctor will not take a picture with so many patients standing.
Yes, ma'am. And they are considering that symptoms just like cough and cold like that.
No, in the Western countries, they regular have the health. We can't afford to. We don't have the time also, because if you have an appointment at 10 a.m., it's highly likely you will not get to see until 12 noon. You will have to sit there. So that's the problem. We don't dare to go.
Yes,
No more questions.
Done, ma'am?
Yes, thank you.
So, I will thank you very much, ma'am, for agreeing to our invitation to share your expertise and with our participants. You have nicely presented from very basics, machine learning, perceptron, and then going towards deep learning. These fundamentals are very useful to apply these things in remote sensing also. So all participants are requested to just go through this, because Professor Biswas has also discussed something related to convolution neural network and other deep neural network architectures. So whenever we are dealing with AI, so these are the very basic concepts. Okay, so all of you are requested to go through it, and in the evening, I think all of you are doing some sort of Python coding. Yes. So use it in your remote sensing applications and earth observations. Okay. So thank you, ma'am, once again for coming from a long way and sharing your knowledge with our participants. Thank you very much, ma'am. Thank you. So at 4 o'clock the tea will come. So you can join it. So maybe in meanwhile you can discuss.
And ma'am, we have a group photograph.
Okay.
Right?
Electrical impedance. Yes. No, the problem is you don't have the data. That is the only problem. EIT, where are you? আমাদের একটা প্রজেক্ট ছিল EIT generation solution, but then they were supposed to generate the data. They didn't do that part, but we were looking for the data. So we just emulated some data. So, I mean, if you are interested, my student can
I will share the shootings. It's in GPS for
the pictures you share.
Yes.
ये वाला तो इसको पीछे कर दो सर रिकॉर्डिंग हो रहा है
According to concept.
चार क्लिक होना है शूट एट मी
Thank you. Good to see you. You're from where? Oh. Hey, Mudunga, how are you? No, how are you? Salted. আমাকে একটা ইমেল দিলে আমি because actually EIT, you know, my student was working on it, but you don't have data. Cannot data, so you can buy some machine and you are in the computer science department here. Electrical. No, you can you can apply for a project with buying that machine. So you can send me an email.
Okay.
I can't connect you to my student. She's my PhD student. She are just about to finish my just a defense is there. The examination report is about to come. So then, but then one of our chapters was based on that project. But then NIT Durgapur, the partner there, they did not generate the EIT data. They could not generate. So the project could not be completed properly. She simulated the data, but if you can, I mean, why don't you go for some project you can buy that machine and generate data. Data is very important. EIT has promised. And it's not harmful also, you know, the radioactivity is not there.
So we are moving to other actually hall. There is some other meeting with the students. So please join with IT for IT at 4 o'clock. Okay?
Oh, is there other meeting?
Yeah, ma'am.
I know.
So this was
What is the meeting about? What is that other meeting about? Oh.
C block. A block. A block is all central. Oh.
The team from और ये जो व्हाट नेम श्वेता उसके बाद
वही तो अच्छा होता ना।
तो लैब करा देते हैं लोग। हाँ 1 घंटा 4:30 बजे। हाँ लैब। आई तो चले।
Right? Yeah. Still the root of Susmita.
Sir, there is nothing special.